Hello, and welcome to a digital differential equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 2.3, Modeling Growth and Decay. In Chapter 2.3, we look at applications of the first order linear differential equation y prime equals ky, where k is a constant. This differential equation is an important model for phenomena in science whose rate of growth is relative to the size of the quantity present. Important applications include growth or decay of a quantity, and interest and annuities in finance theory. To get started with this section, let's look at some definitions. Exponential growth occurs when the rate of growth of a quantity is proportional or relative to the size of the quantity present. The differential equation that captures this is y prime equals ky, where if we're talking about growth, then the quantity k, this constant, will always be greater than 0. Exponential decay occurs when the rate of decline of a quantity is proportional to the size of the quantity present. Notice that the differential equation y prime equals ky is identically the same. However, when talking about decay or decline of a quantity, the value of the constant k will be less than 0. Graphically, we should observe that if you have a growth curve, k is greater than 0, then our exponential growth will look like the exponential function e, where time is greater than 0. Similarly, on a decay curve, where k is less than 0, you'll see an exponential decay curve declining as time goes on. Let's look at some examples or solutions of the exponential decay or growth model. What I would like to do is develop the solution to this decay or growth model now, so that we do not have to solve this problem repetitively. Your general solution will not change from one problem to the next. The general solution of the initial value problem, y prime equals ky, y of 0 is equal to y naught, where in this problem we say that y naught is your initial or starting value. The solution to this differential equation can be found using the integrating factor method or by separation of variables. Here, I'm going to use separation of variables. So remember, our differential equation y prime equals ky can be rewritten in the form dy dt is equal to ky. If we're solving this method, our differential equation using separation of variables, our goal is to get all of the y variable on one side, all of the t variable on the other. In which case, I'm going to multiply to get dt on the right side and divide to get y on the left. This produces the equation dy over y equals k dt. Now that we've separated our variables, I would like to integrate the left side with respect to y and integrate the right side with respect to t. Recall on the left side, the antiderivative of dy over y is going to be the natural log of the absolute value of y. And because we have some improper integral, we would have an arbitrary constant of integration on the left. Similarly, the right-hand side, the antiderivative of k dt would be kt, and because it's an improper integral, I'd have another arbitrary constant on the right-hand side. Now remember when we covered this topic in chapter 1, we said that technically these constants are different, and so we might represent them with c sub 1 and c sub 2. However, in many problems, you may not be differentiating these two constants because you'll be combining them. So in this video, I'm going to continue to differentiate them a little just so we can see this process. If you were solving for y, you'd probably subtract these two constants to get them on the same side of the equation. Of course, this gives us natural log of the absolute value of y equals kt plus c. Of course, if c2 is some unknown constant and c1 is some unknown constant, then here we're saying c is equal to really c2 minus c1. I'm not going to keep differentiating how my constants change throughout this problem, though, and I will just mention how the constant gets changed. If we continue to solve for y, we're going to have to exponentiate each side of the equation with base e. Remember, when we exponentiate the right-hand side, we must have all of this be as an exponent. We did this exponentiation with base e with the expectation that e and natural log are inverse functions, and so that these will cancel. So that we have just the absolute value of y equals. Now on the right-hand side, it's important that we acknowledge that this e raised to this sum can be written as e to the kt times e to the c. Now remember, if c is some unknown constant, then e to the c is still some unknown constant. And so we can write this as the absolute value of y equals c e to the kt. Now, without doing the algebra to verify this, I will ask you to recall in chapter 1.3, we made an algebraic argument that the absolute values in this equation can be absorbed by this constant. This results in the solution, your general solution, y of t equals c e to the kt. This is your general solution. Now, this problem we were given, though, was an IVP. We were told that y at time 0 is equal to y naught. This would be your initial condition. So if we were to continue and solve the IVP, then we would require that when you evaluate your solution at time 0, which would be c e to the 0, this would have to equal y naught, which tells us that c in general will equal y naught, which is whatever your initial value is. And so we get y of t can be written as y naught e to the kt. this is the solution to our initial value problem, where y naught is always the initial value. Now, I'm asking that you remember this general solution so that we can use it for each of the problems that we'll see in chapter 2.3. However, if you'd like to solve this problem, you're welcome to do so. Let's see how this looks with applications. Here, our first exercise. The number of bacteria in a yeast culture grows at a rate proportional to the number present. If the population of the colony doubles in 1 hour, and if 200 are present initially, then let's write the initial value problem. Now with this problem, what I'd like you to observe is the wording grows at a rate proportional to the number present. This wording tells us that we're talking about a differential equation of the form P prime equals QP. Now I chose to use the letter P because we're talking about a population of living things. However, in other problems, you may use other letters rather than P to represent your variable. We also know that because this population is growing, we know that our constant K will be greater than 0. Additionally, we are told that 200 are present initially. This tells us that P at time 0 is equal to 200. This is our initial value problem. Remember, an initial value problem is a differential equation with an initial condition that it must satisfy. We're now asked to find the general solution. Now we could solve this differential equation again, but from our previous page, we know that the general solution will be P of t equals P naught e to the kt. Or if we insert our initial condition, we know P naught is really 200. We have P of t equals 200 e to the kt. This is our general solution. However, notice that what is not written in our equation is what this value of K is. So now we're asked to determine the decay constant. To determine the decay constant, I'm going to use another part of the equation that tells us that the population doubles in 1 hour. Now the fact that it doubles in 1 hour says P of 1 hour would have to really equal 400 bacteria. Remember, we started with 200 initially, and it doubled in 1 hour, so now there'd be 400. We can use this to determine what our value of K would have to be, because we would have P of 1 would be 200 e to the 1k, and we know this has to equal 400. Notice that the only thing that's not known in this equation is what the value of K is. So let's solve for k. To solve for k, you'd probably divide both sides by 200. To obtain e to the k equals 2. You would probably apply a natural log to both sides of your equation. And I choose to apply the natural log with the expectation that e and natural log are inverse functions, so they will cancel, leaving k is equal to the natural log of 2 is the value of our constant. Now, if you grab your calculator, you should be able to approximate the natural log of 2 as 0.693. This is the value of our constant k, which gives us a solution. Well, let's not call it a solution. Let's call it a model. So we'll say our model for our bacteria population will be P of T equals 200 e to the 0.693 t. This is our model that should predict our population growth. Now that we have our model, we can answer questions such as, how many or how much bacteria will be in 5 hours? Here we'd be looking at P of 5, which should be 200 e to the 0.693 times 5. Now, if you grab your calculator, please confirm this with me, but I believe you should get 6395.29, which if we round, and typically when we round living creatures, we always round up, even though this number 2 is less than 5. I'm going to round up and say this is really about 6,396 bacteria will be present after about 5 hours. Okay. Last part of our question. When will the number of bacteria reach 4 times its initial size? Notice here that 4 times its initial size, we started with 200, so we're asking when will the bacteria reach a size of 800? So here we're being asked to find the value of time such that 200 e to the 0.693 t will equal 800. Find the value of time where the population reaches 800. So let's solve for t by dividing both sides by 200. So that we have e to the 0.693 t is equal to 4. Now we want to find t, which is in the exponent, so we need to get rid of our base. And so we choose to take a natural log of both sides with the expectation that the natural log and e being inverse functions cancel. So we get 0.693t equals the natural log of 4. Or lastly, t would actually equal the natural log of 4 divided by 0.693. I'm going to grab my calculator right now. Natural log of 4 divided by 0.693. And I get this to be about 2.0004, which I'm going to say is about 2 hours. It takes 2 hours for our population to be 4 times its initial size. Okay, I hope this makes sense. Let's look at another example. A certain radioactive material is known to decay at a rate proportional to the amount present. Notice the wording there. It decays at a rate proportional. This wording tells me that we're talking about an exponential decay model. Over a 10-year period, an initial amount of 100 grams decayed to only 60. Our first question. Find an expression for the amount of material after t years. So we're not being asked to write the differential equation at this problem. We're just asking to write the amount present after t years. Now, so since we're talking about a material, I'm going to use Q for the quantity of material. So we can say if Q is the quantity present, then we know our solution that models this will have to be of the form Q of t equals Q naught e to the kt, or e to the negative kt. Now you can put the negative here or you can leave it off. I think I'm actually going to leave the negative off for now. However, we should observe that k should be negative, but I'm going to write that separately. So I'm going to write e to the kt, where we should say that k is less than 0. We can also say that because we knew that we started with 100 grams, that we could write this as Q of t equals 100 e to the kt. This would be a general equation that talks about the amount of material present after t years. What we still do not know in this equation, though, is what is k? And k is referred to as our decay constant. So let's find the value of our decay constant. We're going to use the fact that we know that after 10 years, there's only 60 grams left. So this tells us Q of 10 is equal to 60. And leads us to solve the equation 100 e to the 10k, remember t is 10 years, when is this equal to 60 grams? This leaves an equation with only one value not known, and that's the value of our decay constant. So let's solve for k. Let's divide both sides by 100. To get e to the 10k is equal to 60 divided by 10, I think is going to be 0.6. Now we want to solve for k, which is in our exponent, so let's choose to take the natural log of each side, so that we have 10k is equal to the natural log of 0.6. And we wanted to solve for k, so k is going to be the natural log of 0.6 divided by 10. And I'm going to write my answer to 4 decimal places. Now notice when you do the natural log of 0.6 divided by 10, this is going to be negative like we were expecting. It's going to be negative 0.0511. And so that we get k is negative like we were expecting it would be. This gives us our model. Our model is going to look like Q of t equals 100 e to the negative 0.0511 t. This would be a model that should be describing the decay of this radioactive substance. Okay. Our question: how much will remain after 100 years? Here we want to figure out what is Q of 100. So let's evaluate our function at 100. I'm grabbing my calculator so I can evaluate this. And I get 0.604 grams is how much of this radioactive material is left after 100 years. It's decayed from an initial quantity of 100 grams to 0.604 grams. Okay, let's calculate the half-life of the material. Now the half-life of a material is going to be the time required for the material to decay to half of the initial size or the initial quantity. So, put it another way, we're asked to find T such that Q of T equals 50. The amount of time for it to decay to half. Now that gives us the equation 100 e to the negative 0.0511 t equals 50, where we want to solve for t to find the amount of time it takes for 100 grams to decay to 50 grams. The half-life. So let's solve for t. Again, let's divide both sides by 100 to obtain e to the negative 0.0511t equals 0.5. We will take the natural log of both sides with the expectation that the natural log and the e being inverses will cancel to give us negative 0.0511t equals the natural log of 0.5, which makes t equal the natural log of 0.5 divided by negative 0.0511. So grab your calculator to determine what t has to be. I get, if I go to 1 decimal place, about 13.6 years is your half-life. The amount of time it takes for this substance to decay to half of its initial quantity. Okay. Last question. When will the material decay to 25 grams? Notice that the algebra we're here for solving this question is going to be very similar to our previous problem. We were determining the half-life, the amount of time to decay to half of the material. Now we want to figure out the amount of time to decay to 25 grams. Either way, we're still asked to solve for time. This set of algebraic steps is going to be something that you will do commonly in this homework assignment and to see these problems. So you'll become very familiar and maybe come to a couple shortcuts. But if you're solving for t again, you got to divide both sides by 100, which leaves e to the negative 0.0511 equals 0.25. We'll take a natural log of both sides. To obtain negative 0.0511t is the natural log of 0.25. Or t is equal to the natural log of 0.25 divided by negative 0.0511. Which, if you're confirming my calculations, this should be about 27.1 years. Now, this value should not be surprising to you based on our answer in part D. If it took 13.6 years to decay from 100 grams to 50 grams, then in another 13.6 years, it'll decay from 50 grams to 25 grams. So notice that if you double 13.6, you do get almost 27.1. We are off a little bit due to rounding error. Okay, let's try another problem. Radiocarbon dating. By chemical analysis, it has been determined that the amount of carbon-14 remaining in samples of burnt charcoal at an archaeological dig was 15% of the amount such trees would have contained when living. The half-life of C14, the amount of time required for the given amount to decay to 50% of its original value, is approximately 5,600 years. We're also told that the quantity of C14 in a charcoal sample satisfies the decay equation. Let's write the initial value problem. So here our initial value problem would be Q prime is equal to KQ, where Q of 0, our initial value, would be Q naught, and our value K, our decay constant, we know would be less than 0. Now, this problem differs from the previous problems in that they told us specifically what Q naught was, our initial value. In this problem, we're not explicitly told what Q naught is. However, you could make the claim that Q naught is equal to 100% of C14 that would normally have been living. So you don't know the actual amount in grams, but you do know it would be 100% of what was living. This allows us to write our general solution, Q of t, as either Q naught e to the kt, or if you want to, write it as 100% e to the kt. But this would be your general solution. Let us find the value of the decay constant. Here we're going to use the fact that we know Q of 5,600 years is equal to half of the initial quantity. So half of Q naught. This leads to the equation to ask us to find T, find K knowing that our decay equation, Q naught, e to the 5,600 K has to equal to half of its initial value. Now, if we're solving for K, notice that we could divide both sides by Q naught so that they cancel. This leaves us with e to the 5,600K equals 0.5, where we choose to take a natural log of both sides of our equation with the expectation that natural log and e will cancel as inverse functions to give us 5,600 K is the natural log of 0.5, or that K is equal to the natural log of 0.5 over 5,600. Now, I'm going to write my value, my approximation to K, to 6 decimal places here to get negative 0.000124. Now, depending on the amount of rounding you do here, you could get a slightly different answer. But with this value of K, we can write our decay model as Q of t is equal to Q naught e to the negative 0.000124 t. This is our decay model. And lastly, we're asked, what is the approximate age of the charcoal dig? So remember it said earlier that the charcoal, the burnt charcoal, had 15% of the amount of C14 that there would be if the charcoal had been, if the tree had been living. So it's 15% of what it should have had. This allows us to say find T such that Q of T is 15% or 0.15% of what it would have had initially. So 15% of Q naught. Okay, this gives us the equation. We want to find out when does Q naught e to the negative 0.000124 t, when is this equal to 0.15 of Q naught? This is what we'd like to solve for to find t. So notice that the Q naughts will cancel, leaving e to the negative 0.000124 t equals 0.15, where we choose to take a natural log of both sides of our equation, with the expectation that this natural log and this exponential will cancel, leaving negative 0.000124 t is equal to the natural log of 0.15. Or if we're solving for t, t is going to be the natural log of 0.15 divided by negative 0.000124. Now, if you grab your calculator to confirm this, I believe natural log of 0.15 divided by negative 0.000124 should come out to be approximately 15,299 years. Would be the age of this charcoal. Okay, let's try one more question. This will be the last one I have for chapter 2.3. And this is one of my favorite questions. As I'm a scuba diver, I love to go in the ocean and go scuba diving. So here it says, the fact that sunlight is absorbed by water is well known to any diver who has dived to a depth of 100 feet. Now, just so you're aware, 100 feet is incredibly deep when you're thinking about diving as a recreational diver. Most interesting things in the ocean happen between 20 to 40 feet. So 100 feet is very deep. It is also true that the intensity of light falls exponentially with depth. Suppose that at a depth of 25 feet, the water absorbs 15% of the light that strikes the surface. Now our question. At what depth would the light at noon be as bright as a full moon, which is 1/300,000th as bright as the noonday sun? Now there's a lot of wording in this question, but let's see what we can pull out of this. We are told about the model initially. We are told that the intensity of light falls exponentially with depth. This tells us that Q prime is equal to KQ, where Q of 0, and that's probably your initial depth, would be 100% of your light. But for simplicity, let's just say this is 1 as a decimal. We also know that our general solution for this would have to be Q, and I'm going to write D for depth, because this time we're not talking about time, we're talking about depth. So here our general solution be our quantity of light at any depth is going to be 1, our initial value, e to the kd. What we need to be able to first do is be able to find our decay constant k. Now we should observe that k has to be 0 since we're talking about a decay model. To find k, we want to use the fact that at 25 feet, the water absorbs 15% of the light, meaning that Q at 25 feet, and be cautious here, if it absorbs 15% of the light, then there's actually 85% of the light remaining. Oh, I wrote a decimal and a percent. I should probably just write, say, 85% of the light remains. But we should probably write this as 0.85 as a decimal. So this leads us to find D, or find K, excuse me. It's going to be 1 e to the 25k, where we're letting our depth D be 25. So it leaves k as the unknown quantity. Has to equal to 0.85. So we will, although the 1 is not necessary, let's just not write the 1. E to the 25k equals 0.85. And we'll choose to take the natural log again of each side, with the expectation that the natural log and the e being inverses will cancel. So we'll have 25k equals the natural log of 0.85. Or k is equal to the natural log of 0.85 divided by 25. And double check my calculations, but I believe this should give us a quantity k. Remember, we thought k should be negative. It should be negative 0.0065 when you go to 4 decimal places. This gives us our model. Q of D is 1 e to the negative 0.0065 d for depth. Now let's go back to our question. We were asked, at what depth? So our answer is going to be an answer for D. At what depth would the light at noon, which we said was 100%, be as bright as the full moon, which is 1/300,000th as bright? So what you'd like to visualize with this problem and I'm going to do my best artwork I can with this. If here is the sun at 12 noon, striking the surface of the water, that we know that once you go down to a depth of 25 feet, there's only 85% of your light remaining. We're asking, how deep do you have to go so that it's 1/300,000th as bright as it would be at noon? So we're being asked to find that depth D. So that find that depth D such that 1e to the negative 0.0065 d is equal to 1/300,000th of your noonday sun. Notice that we're solving the algebra problem, the same algebra problem lots of times. So this will seem like a pattern now. We'll choose to take the natural log of each side to obtain negative 0.0065 d is equal to the natural log of 1/300,000th. And I'm going to avoid writing this as a decimal right now because of rounding error. I can leave it as 1/300,000th there. So that d is going to be the natural log of 1/300,000th divided by negative 0.0065. So grab your calculator to confirm I'm doing this correctly. The natural log of 1/300,000th divided by negative 0.0065. If I round this to the nearest foot, I get this to be 1,940 feet deep. Notice that this is almost half of a mile. A mile is 5,280, so this is nearly half a mile deep. If you go a half a mile deep, it's going to look like it's, what would it say? It's going to look like it's as bright as a full moon. So it's going to be pretty dark, half a mile deep. It's going to be as bright as it would be under a full moon. Okay, I hope this helps you with everything that you need for your homework for Chapter 2.3. I hope this is helpful, and I'll see you in our next video.